So as we alluded to in the previous lecture, when you shine light on this molecule that has A and B to do a 6-pi electrocyclic ring closing reaction, you actually get the opposite diastereochemical outcome. And you go through, in this case, conrotatory rotation to get there. So why is that the case? Why do you get the opposite outcome when light is being used to induce the reaction? Let's kind of start capturing that. Well, it has to do with how the light is interacting with the molecule to provide energy to the system. When light provides energy to the system, it encourages the reaction through electronic excitation. So light provides energy and causes electronic excitation. Okay, electronic excitation. So we've seen excitation before. This happened in our spectroscopic absorption events. When we shine light on our materials, we saw things kind of go from a ground state to an excited state. That was an excitation. Ground state, excited state. We went through excitation. It took the right photon to get there. The same thing is happening here. In electronic excitation, the electron is pushed to higher energy levels. So it's pushed to higher energy levels. In particular, for electrocyclization reactions, excitation forces an electron from the highest occupied molecular orbital, the Homo, to the lumo. So you excite the electron from the Homo up to the lumo. Okay. Now what this does is, I mean, we could consider this in all sorts of ways. Let's keep it simple and consider the molecular orbital diagram only including the orbitals we care about, those frontier orbitals, the HOMO and the LUMO. Now in each of those, in the 2 electrons of the highest occupied molecular orbital, let's put the HOMO. And what we're saying is that unlike heat, what we're doing with light is we are pushing one of the electrons from pi 3 to pi 4. And we maintain some spin consistency here. So if we started down, we have to keep it down. If we started up, we have to keep it up. They're still spin paired. Quantum mechanics says so. But what this means is that for pi 4, which was the LUMO, think about the definition of the LUMO now. The LUMO is the lowest unoccupied molecular orbital. Pi 4 is no longer unoccupied. It has an electron. It's occupied. In fact, it's the highest energy orbital that's occupied. So we cross that out. That is no longer the LUMO. That's the HOMO. And if pi 3 was the HOMO, it's no longer the HOMO because it's not the highest energy orbital that has electrons. There's pi 4. Pi 4 has one more node. It has higher energy and it has electrons. Now what this means is we have to consider a different arrangement of orbitals to understand how the electrocyclic ring closure occurs in the presence of light. That is to say, what does pi 4 look like? Well, pi 4 was, first of all, an antisymmetric. So the left looks the opposite of the right, antisymmetric with, so we start with 0, 0 for 1, 2 for, we have 3 nodes. with 3 nodes. Let's just put it that way. So if we consider what pi4 molecular orbital looks like in terms of its p orbitals, we have to get to 3 nodes and we have to be antisymmetric. And this is the one where we go 1, 2, 3 both the same, 4, 5 both the same, and 6 down. This gets us to an antisymmetric orbital where the left is the opposite of the right through bilateral symmetry. Like you could, yeah, anyway, they're antisymmetric. I won't try to tease out a definition of that. And we have nodes here, here, and here. Antisymmetric molecular orbital with 3 nodes. Now what I want to focus on is not all those lobes in the middle. I want to focus on the p orbitals at the outside of our molecular orbital, right here and right here. And I want to consider these orbitals when I construct the kind of 3-dimensional molecular orbital so that we can see how things twist and turn and see why things go conrotatory with light. That's the whole goal here. We want to see why we're going conrotatory with light. So here's my hexatriene. And now I've got my orbital here, and we're antisymmetric now with pi4. These are going to be pi4 terminal orbitals. So, I mean, we could draw all of the other p orbitals if we wanted to. We don't have to, though, because it's the end caps that we care about. It's the end caps that twist into each other to get to head-to-head overlap to get to a sigma bond. So let's consider, what's it going to take to get overlap to occur? Well, if we want the shaded lobes to overlap, we could go clockwise in this direction and then clockwise here, because if we go clockwise there, we're going to spin up this darker orbital. I'm going to make that less kind of, anyway, if we're just spinning that, I'm just showing an arrow going from the opposite direction, or that continuing on in that same direction, excuse me. So they're both going clockwise. They're both clockwise, and that's conrotatory. They're both clockwise, so conrotatory. Now what that results in, after we do the 4 pi electrocyclic ring closing reaction, is that we get to something that looks like this. So again, I chose to have my shaded lobes overlapping with each other. And I could draw the pi bonds, the other pi bonds in the product. So I chose to have those shaded lobes overlapping with each other. But now that we can see them overlapping with each other, this is where our new sigma bond forms. So our new sigma bond forms here. And that's because I used pi4. And pi4 was an antisymmetric orbital because it's an even numbered orbital, I guess. So it's antisymmetric. So they were going in the opposite directions, requiring us to go conrotatory rotation to get to the orbitals, to allow the orbitals to overlap with each other. Now, what does that mean for our substituted molecule with substituents A and B? What happens? Well, if we consider now the addition of substituents A and B, and we again have our terminal p orbitals from our pi4, now the HOMO after electronic excitation from light interacting with the molecule, we can do the same thing where we twist and we twist. Those are going in the same direction. It's just I'm at the underside for the right side. This is conrotatory still. Both are clockwise. I mean, I could continue on this way. But anyway, what happens then? Well, I've got my lobe up for A, and I've got my lobe down for B, and I need to twist them in the same direction to get the lobes to overlap. And what that means for A and B is that A is going to twist up, and B is going to twist down. So we have clockwise for A and clockwise for B. They're both twisting in the same direction. That is conrotatory rotation. And as a result, one is up and one is down. Our lobes are shaded, have in-phase overlap to show the formation of a new sigma bond. Recall, we could have the light lobes. We could actually go in the opposite direction, both clockwise. That would result in the enantiomer. Or, and I'll draw the double bonds here, we could have the light lobes overlapping with each other. And then we could have A on the bottom and B on the top. So both could be counterclockwise for the enantiomer. Okay, so something sort of universal emerges from here. And that is, when we look at this, it's with light, we're going to see the HOMO and the LUMO sort of determine which direction we're going to turn things. And actually, what's cool about this is if we add one more, if we make the number of pi bonds even, we actually flip everything. If we make the number of pi bonds even, then using heat, we'll get conrotatory rotation, and light will get disrotatory rotation. So let's say we use a 4 pi electrocyclic ring closure. So I'm going to look at 4 pi electrocyclic ring closure with light and heat. Now to do this, I need to consider the HOMO and the LUMO. So the HOMO is going to be pi 2, which looks like this. Now we only had 4 pi electrons in butadiene, our just 2 alkene system. So with the 4 pi electrocyclic ring closure, we did something like this. Sorry. Okay. So it was pi 2. Pi 2 has one node and it's antisymmetric because it's an even numbered node, or it's an even numbered molecular orbital. So one node, antisymmetric. That is, the left is the opposite of the right. Okay. So there's our HOMO. And our LUMO is pi 3. Now we have a symmetric molecular orbital because it's odd numbered and we have 2 nodes. So node there for 2 nodes. Okay. So these are the 2 orbitals that we have to consider when we're using heat. We'll use the original HOMO that we start with, and with light, we'll use the LUMO. What was originally the LUMO. Electronic excitation will convert pi 3 into the HOMO. But let's just consider the termini here. So the termini for, let's say we've got a system like this, A and B, going to A and B. We have 2 new stereo centers being formed. How do we understand this? Well, if we consider the molecular orbitals, A and B. So with heat, we're going to use pi 2. Pi 2 is going to look like this. And so for pi 2, to get in-phase overlap to occur, we need to actually rotate both orbitals in the same direction. I'm showing clockwise here. And if we do that, we get the dark lobes to overlap with each other. That's again because we have an antisymmetric molecular orbital. And so just rotating it in the same direction will allow for in-phase overlap to occur. And what that means for A and B is, well, if you kind of, one's sticking out, the other one's sticking out one way, this one's sticking out this way. They both move in the same direction. Ugh, breaks my wrist. One's going up, one's going down. So A and B. Now, if we want to use light, then we have to use what was originally the lumo, and that's pi 3, which is a symmetric molecular orbital. If we have A sticking out over here, B sticking out over here, for us to get in-phase overlap, we have to rotate the termini in opposite directions. So to do that with light, we've got A and B sticking out as my thumbs. They're going to rotate in opposite directions. I'm bracing my wrist for another fracture, but actually we're moving in opposite directions. So if one goes this way, this one goes this way. Now I could make it really hard on myself. I'm both go the other way, but that's just the enantiomer. And I know I formed that because it's a pericyclic reaction. So instead I'm just going to consider going both up because it's comfortable. And so if they both rotate, one rotates, in this case, A rotates clockwise, B rotates counterclockwise, we're going to stick both of these groups up. So A is going to go up, B is going to go up. So what that means for our reaction is, I'm going to show it in the middle and kind of go left and right. But if we have A and B and we do this reaction under heat, we get the trans relationship where one is up and one is down. It doesn't matter which because you get the enantiomer. Or they're both up in the case of light. So in this case, with heat, we actually went conrotatory, and with light, we went disrotatory. And what it had to do was the symmetry or antisymmetric relationship of the molecular orbital, okay? So whether or not it was a molecular orbital being symmetric or antisymmetric determined whether or not we would go conrotatory or disrotatory. And that has to do with the number of pi bonds that we have, it turns out. So there's a general rule of thumb. The general table, it's not really a rule of thumb, it's a table. And I like this table a lot, where what you do is you go con, dis, con. And so what this is a table that says you either go conrotatory or disrotatory, whether or not you're using heat or light. So it goes heat, light, and then whether you have an even number of pi bonds or an odd number of pi bonds or pi bonds. So even and odd, this refers to the number of pi bonds that we're considering doing. So if we're doing a 6 pi electrocyclic ring closing reaction, that's considered to be an odd numbered pericyclic reaction under this table because it uses 3 pi bonds to accomplish the transformation. So we can use this table now without ever having to build a molecular orbital diagram, which is really useful for more complicated examples. So let's go ahead and put this to practice. Let's say we've got this molecule. Now I'm going to take our usual molecule and spin it on its head. I'm going to make A here, Z, and then B, E. And I'm going to apply heat. In that case, it's kind of like we have A shooting in and B shooting out. I really like my thumbs to be the end caps. These are like the ends of my pi system, and they could either go conrotatory, disrotatory, or let me try that again. Conrotatory or disrotatory. Okay, so with heat here, we have an odd number of double bonds. So we're in the odd category and we're in heat, so we must go disrotatory. So I've got A and B. One's going to go this direction, the other one's going to go this direction, and they're trans to each other. So I can draw the product and say to myself, what's the stereochemistry? Well, with disrotatory rotation and having one thumb in, this is my Z alkene for A, and one thumb out, Disrotatory goes, one goes up, one goes clockwise, the other one goes counterclockwise. It's not about one going up or down. It's about clockwise or counterclockwise rotation. So in this case, it happens to be trans. But if I did the same thing for an 8 pi electrocyclic ring closing reaction with octatetraene, not cyclooctatetraene, but octatetraene, and I apply heat to this, then according to my table, first of all, I'm even because I have 4 pi bonds, whereas before I was odd because I had 3 pi bonds. So I can have A in, B out. I can think to myself, okay, heat with even is conrotatory. So if one goes this way, the other one goes this way. They follow each other. They rotate in the same direction. It doesn't mean they have to be on the same side. They just rotate in the same direction. Recall, they were both shooting outwards and they both rotate in the same direction. One was up and one was down. Here, they rotate in this, they rotate in the same direction. They go together. In this case, I'm going to draw the product where they're both up. Okay. What's critical about solving these problems is you first have to be able to push the arrows and draw the products. Speaking of which, I think I got the other one on, right? So if I went this, yeah, what am I doing? I said it was trans several times and I drew a wedge. I'm sorry about that. Like I said, the first thing you have to be able to do is connect the bonds and then worry about the stereochemistry. But the molecular orbitals can get there and they can help you out, especially when you're in a jam and the structure gets complicated, because you might remember that an 8 pi electrocyclic ring closure is followed by a 6 pi electrocyclic ring closure. That is, if I still heat this, I went from 4 pi bonds to 3 pi bonds in a subsequent 6 pi electrocyclic ring closure. That's odd. And whereas before we were conrotatory, now we're odd, so we're disrotatory under heat. I push my arrows. I need to connect this bond to this bond to make a 6-membered ring connected to a 4-membered ring. Now the 4-membered ring's got A and B, both as wedges. But what about these stereocenters? Well, if we're disrotatory, let's imagine my fists are the dots. They both have substituents pointing in towards the ring, right? This is the rest of the ring. So they're both pointing in, so I need to do disrotatory. So if I put one down, these are going together, so I have to go opposite. I'm going to push this one up. I'm going to push my left one up. If my left one's going up, then this one, instead of rotating clockwise, is going to go counterclockwise. And they're both going to be up. Oh, well, that's easy enough. So they're both going to be up or both down. Just as long as you focus on one pair of stereocenters at a time, you will get it. So I'm going to draw a wedge. I'm going to make this ultra awkward and draw a wedge into another wedge. It would have been easier if I had instead drawn the dashes on the hydrogens, but I don't want you to worry about that because the dashes on the hydrogens communicate the same thing. I just want you to effectively determine the cis-trans relationship amongst the groups. And so I just want to make sure I got this. Yeah, I got it. Did I get this right? So they're both down or they're both up. Okay, now disrotatory, if one goes up, one goes this way. Yeah. Okay, I'm just looking at my notes from last year. Looks like I got it wrong. Okay, well, maybe I got it wrong this time, but I can't find it now. Okay, anyway, that table will help you solve the stereochemical outcome for the electrocyclic ring closing reactions. Be sure, though, that you can push the arrows and make the product effectively first. And A and B could be anything. They could be chlorine atoms. We could have methyl groups on the rest of the molecule, but those aren't going to be affected because the only places we form stereocenters are at the end of the molecule. Okay, let me know if you have questions on this. This stuff can be kind of fun. Use your thumbs effectively, that sort of thing. Okay, for this one, we'll end here and we'll call it good on electrocyclic electrocyclization reactions. Okay, have a good one, everyone.